Hey guys, today we'll be talking on something very interesting, especially if you have been working on artificial intelligence, then you must be knowing about min-max and alpha-beta pruning. So there's a optimization on alpha-beta itself, which is called the dangerous killer heuristic. It's much more simple than it sounds. What it does is it uses contextual information rather than your heuristic evaluations to find the best move. Now, as you know, alpha beta, what we do is we sort the moves according to their strengths. So in fact, in inverse order of their strengths. So the strongest move is always taken first. The reason for that is you want to evaluate the strongest move and you want to see in case it gives you an alpha or a beta cutoff. Because whenever you get a cutoff, you can actually ignore the other moves. You can get rid of evaluating the moves that would result from this position. One of the things to notice here is that in many games, one particular move for a given scenario, for a given move index, is so strong that irrespective of what your reply is, that move is the best. And let's take an example. Let's take something simple like X and O's. Now imagine X has played in these two positions and O has played in this position. What happens here is that it's O's move. What O wants to know about is what is the best move, but there are lots of possibilities. O can play here, O can play here, and everywhere basically. Now if you program something like this, your heuristic might be inaccurate and it's not feasible to calculate for every possible move and every possible response of X and O. So let's assume that you had an O here and your heuristic was lucky and you went for X here. This is a winning position for X, and what we say is that X has a killer move here. This move on 3,1 is a killer. Now O says I can't play on 2,1 because that's a losing move. So O tries a move here. Its heuristic might say that X should play here. But the situation tells us that X has a really, really good move in the previous scenario over here. So that's what O is going to look at. He's going to actually think about X playing the move here. The reason being, the concept is that irrespective of the scenario, for this particular move, we should evaluate something which is very dangerous to us. So that's what O will evaluate, and it will realize that it's losing again immediately. So what you did is you didn't waste your time evaluating responses like this, evaluating nodes like this. What you did is just backtrack, immediately give up, and hence you have saved time. The only possible thing that actually makes sense over here for O is to play here, and that's the only one which is actually blocking the killer move. So that will be evaluated further. Now, this kind of thing is very interesting because I have used it recently in the artificial intelligence that I've been programming, and the performance of the programs really boosts up. But of course, there's stronger evidence that this is really good. Chess machines, chess engines actually use this very often. They use a slightly more advanced version of this called the history heuristic. So, but we'll be looking at the killer heuristic. It's very similar, and in fact you can just read up on the history heuristic and it's not going to be too different in terms of the core idea. So how we are going to do this is that we have a game tree, right? Now assume that this is move 0, that means this is move 1. These are the positions game states at move 1. There is move 2 game states. Now what we are going to do is that per move number, we are going to store a list of killer moves. That ends up looking something like this. You have a list which is serial number or move number, you can call it, of 1, 2, 3, and so on up to the depth that you want to search, and each index points to a list of moves, of killer moves actually. So this is a list of killer moves. Now, whenever you play move 1, you're going to go through this list first. Remember that in alpha beta, we have a list of possible moves and we try to sort it according to the heuristic strengths. What you're going to do is you're going to take the killer moves first, you're going to append it over here, or you can basically take a set and merge these two sets, but just make sure that these killer moves are at the top of what you're searching for. Typically killer moves are very small. The number of killer moves that you actually test are very small because you don't want to waste too much time. So 2 is the size that I have tried, but yeah, 2 is actually enough because that's what practically makes sense for a killer move. So what you do is you just append these 2 moves at the top of the list in your entire all possible move array, and you try these 2 moves first. What happens if this move is not that good? So it was a killer move, but it didn't perform as expected. It did not give you a cutoff. What do? Well, we need to keep this data structure as efficient as possible. What we want is the strongest moves here always. So when we want to add a move over here, we just add to the end of the list and we assign a certain weight to it. Maybe weight 1. If a move is performing poorly, if you tried it and it didn't give you a cutoff, you can reduce its weight by -1. And when the weight goes less than 0, you can actually eject it from the list. What you are essentially doing is keeping a sorted list over here. So you can actually keep a heap. But then there are so few moves actually that usually I prefer to just keep it a list and a sorted list itself. But you can keep a heap, yeah. And so on and so forth. For the second move index, you'll have the same heap configuration. For the third, you'll again have something different. Now, important to notice is that not all moves have, not all move indexes have the same killer moves inside them, because that would be insane. Let's take the scenario of this, X and O's. X has played here and here, and O has played here and here. Earlier we evaluated when O wants to, now it's X's move. So X should think about a killer move, but it shouldn't think about playing a move here to stop O. To just play the move here, this is the new killer move it has. So at move 5, which is somewhere over here, we have a killer move 2,3. So guys, to summarize, we can say that killer moves are actually very simple to implement. It's just per move you store a small data structure of list and the moves itself. So the performance benefits it gives practically are pretty high, and I would suggest you go and read about the killer move heuristic, because in case something is not working, and we try all sorts of optimizations when we are going for game playing programs. This optimization is actually something that you should invest your time in. And let's talk about the implementation now. If you compare with alpha beta, there's just a few more operations and variables that we require. Firstly, killer moves is an array that we are going to store for each move number. There's this array is going to be maintained like a set, so that whenever we are appending or doing any sort of manipulation with it, all the moves in it are going to be distinct. There's also operations that get moves and evaluate. These are exactly like alpha beta, except that we are just going to add some functionality to these 2 functions. So get moves, it takes all possible moves, takes sorts them according to the heuristic strengths, and then you get these sorted moves. What you do is you append the killer moves for that move number to the sorted moves, and now you have a set of moves which you can return. On the other hand, evaluate in alpha beta is a little more complicated. There's a board, a move number, and these 2 parameters that you pass in along with which player is making this move. So you get the moves like we discussed earlier. For each move, you compute a score for the other player with the same alpha beta, but you make the move on that board and then you compute the score. Now, remember that alpha is the minimum that you're willing to take and beta is the maximum that you are willing to give. So minimum that you're willing to take is always for the first player. So if you're player 1, then you're going to update alpha only if the score that you're getting is actually greater than alpha. So you can get more. So the minimum that you're willing to take will be even more, which you're going to set here. Similarly, the maximum you're willing to give should go on reducing if the score is less than beta. The beta will be updated here. This is exactly as per alpha beta. Just there'll be 2 possible scenarios added for killer moves. Let's look at that. So there are only 2 possible scenarios we can have. One is that either alpha is greater than or equal to beta. This scenario means that there's a cutoff. Now, in a cutoff, as we know, we need to add a killer move, or we need to increase the move of the weight of that particular killer move. So that's what we're doing here. We see if the move is contained in the list that we already had. If that is the case, then we come here and we increase that weight. If not, then we just add it to the list that we need to maintain for that index. On the other hand, if alpha is less than beta, this means that there's no cutoff and we need to actually evaluate the nodes after this also. What we do is we see if we were expecting this move, basically if this move was a killer move. If it's a killer move, we are expecting a cutoff, we didn't get that, so we are going to decrease the weight. Now, what this does is it only increases your probability of actually reducing the number of moves that you're going to evaluate. By maintaining this list, you're seeing that overall complexity of alpha beta is not being affected, but it's making a serious additional bonus value in your original min-max algorithm. So, and practically, of course, I've seen my program play much better once I add a decent list of killer moves.